There's actually quite a short talk, it's only a 10-minute talk. It's more or less just an advertisement for our Granite geochemistry database. Hopefully we'll get on to say a bit about some simple some observations we can make just using simple Granite geochemistry. Now this is obviously a Craton-wide project, but it's probably particularly relevant to the southwest Yilgarn at the moment, because this is the area over which over the next few seasons we expect to see the greatest increase in the number of data points. So stay tuned. Hopefully over the next few years there'll be some quite fundamental insights coming out of this data set. At the moment, the number of data set at just about tipping 10,000 samples. Most of these samples have been analysed by us or reanalysed by us. About just over 7,000 of those samples can be classified using are on rocks that are fresh enough. And the analyses are good enough that we can classify them using our sort of automatic geochemical classification scheme. There's another 2,000 analyses we can add to that if we relax our alteration filters a bit. We can analyse. We can add them to the. We can quite confidently add them to the data set. And then there's an odd 700 fairly hopeless analyses, most of which are collected by structural geologists. In terms of an expanding data set, certainly from the analytical perspective and the data spatial coverage perspective, this is becoming a really exciting data set. What really does excite me about this Granite data set is particularly when used in conjunction with the isotopic data sets that Jungs are producing, and all of the new geophysical data sets that the survey is producing, we can really make some really fundamental insights into the compositional and structural architecture across the entire lithospheric column. Why granites are so useful in this respect is I don't really expect you to take note of all of the different classifications of granites that we've got, but the combined source regions of all of those granites, as I say, that spans the entire lithospheric column. So we have granites, the snookatoids and their cohorts. They're derived from the lithospheric mantle peritic sources. A lot of the TTGs, high calcium granites, are derived from lower crustal mafic sources. And the remaining granites, a lot of them, they're derived from more mid to upper crustal mafic and modified mafic sources. So it covers the entire lithospheric column, and each of these specific granite data sets carry with them geochemical proxies, geochemical signatures that are diagnostic of their source region. They also carry proxies that are diagnostic of the depth of melting. They carry proxies that are diagnostic of the temperature of melting, the fugacities of melting. And because a lot of these granites are structurally introduced, a simple map of the granite distribution shows you variations, or shows you the locations of specific magma conduits and so forth. And then there's the metal fertility information that a lot of these granites carry. Certain of these granite types are specifically implicated in a lot of mineral systems, being felsic rocks. The mineral systems we're talking about are gold, base metals, lithium. You can expand that to include rare earth elements, niobium, tantalum, and again these granites carry proxies that tell us about the respective fertility for those metals, and Jung's been doing a lot of work in this space as well. So given that, when we see compositional gradients like this on a map of granite distributions, and we can produce with a database we can produce numerous variations of these diagrams, when we see these sorts of gradients, whether they're sharp or a bit more diffuse, we can come to two conclusions straight away. First of all, these gradients are really significant. They mean something, right? And because the compositional variations we see in these maps, the compositional variations that result from emplacement level igneous processes at this scale are basically meaningless, okay? So that means that the variations we see are a direct reflection of architecture or of processes affecting architecture. So granites provide a very, very powerful, even on their own, a very, very powerful window into source regions. Now, in the time remaining, I just want to concentrate on a couple of specific types of granites that are particularly of interest to me. So now here we're looking at the high calcium, really strongly sodic, high strontium yttrium granites. So the high calcium component of that classification, the high calcium strongly sodic component, that's a proxy. That's a source proxy, and it tells us that we're coming from that these things are coming from a mafic source. The high strontium yttrium is a depth proxy. It tells us that melting is deep. So these are our deep melts of lower crustal amphibolites. These are our quintessential TTGs, the real fair dinkum TTGs. And if you look at the distribution of these, it's quite interesting. They're quite provincial in their distribution. They're very large areas of the Yilgarn where we don't see any at all. Where we do see them, they're quite strongly structurally controlled. They come along shear zones that represent the boundaries between greenstones, or they come along structures within greenstones, and they're more structurally controlled than any other major set of granites that we see. So here we're seeing these granites are also TTGs, but they're coming from slightly dirty compositions or slightly higher up in the crust. We don't see the same structural control. We look at low strontium yttrium granites, so these are granites that are coming from mid-crustal to upper crustal sources. We don't see the same structural control. Our low calcium granites, they come from mid-crustal sources of various dirty granite source regions that contain both amphibolites and reworked felsic crust. Again, we don't see the same sort of structural control that we do for the really sodic high calcium granites. The only case where we do, and I just had to put this in because we can't have a talk on granites without having snookatoids and emphasising the love affair between snookatoids and gold for whatever reason that occurs, and also for the fact that love affair still does seem to be relevant down in the southwest as well. But if we look at the distribution of the snookatoids, it exactly mimics the distribution of the really sodic high strontium yttrium granites. And the other thing about both types of granites is that there's a direct spatial and temporal relationship between them and greenstones themselves. So this begs the question: is there a direct generic relationship between greenstone formation and strongly sodic TTGs and snookatoids that's not shared by the other types of granites? And if there is, in there somewhere are huge implications in terms of crustal evolution, but not only that, also in terms of gold prospectivity. And the relationship with for the high calcium granites is to the extent that those regions in the you and me terrain where we get very, very few high calcium granites, you can start speculating about where we might sit in terms of the structural level. Are we in fact in the root zones of recently eroded greenstones in those along the structures along which a lot of the mafic volumes that fill the greenstone belts were intruded? The other thing I want to quickly look at is just comparing the high strontium yttrium sodic TTGs with the low calcium granites. Low calcium granites have been widely implicated as the potential source region for lithium pegmatites. So when we superimpose them, we actually see that there's quite an antithetic relationship. Where we get the high calcium sodic granites, we don't tend to get the low calcium granites, and vice versa. And we get a lot of these, what you could call paired belts. A lot of contacts between linear outcrops of the high calcium granites and the low calcium granites, because the high calcium granites are associated with greenstone belts. These paired belts are typically along greenstone belts. And we can do a bit of a linesman job on this, a bit of a shonky linesmanship, and come up with just highlight a few of these belts. I've done that in yellow so you can't see them. And then we can drop on there. Now what I'm doing here on your left there, all of low calcium granites for which we have lithium data. The size of the dot's proportional to the concentration of lithium. And on the right, I've taken away all the ones that have less than 40 ppm. So that's already 10 ppm above the regional, what we would consider anomalous. And so we can see that along all of these areas where we have these boundaries between the high calcium granites and the low calcium granites, these are also the zones where we have highly anomalous concentrations of lithium in the low calcium granites. And it's a well-known empirical observation that lithium pegmatites tend to occur along the contacts between greenstones and granites, and we don't know why, whether it's just a reflection of the structural level that we're sitting at, or it's a particular favourable structural regime. But we're not looking at lithium pegmatites here, we're looking at lithium in low calcium granites. And so there's a possible alternative explanation for that, and that source enrichment in lithium in the source of low calcium granites may also have something fundamental, so have some fundamental relationship to the formation of to the earlier formation of greenstones themselves. So I'll leave it there.